Hello, I am Sudhir Deshmukh, PhD student working under Dr. Sunita Dhole, Department of Computer Science and Engineering, DIIT Pune. In this video, we will cover face recognition pipeline, face detection, and Eigen Fcaes. Face recognition is a chain of complex computer vision tasks. Several machine learning algorithms are chained together into a pipeline to construct an efficient face recognition system. The first step in this pipeline is to detect and extract faces from the entire image. The so-called face thumbnail is then passed to the next step in the pipeline, which is to identify facial landmarks such as tip of the nose, mouth, eyes, eyebrows, jawline, etc. These landmarks are then used to find an affine transformation between the template and the input image. The input image is then warped with the help of learned affine transformation, which in turn takes care of the head position in the image. The next step is to encode this warped image into a set of numbers which represent the facial features of the person present in that particular image. These numbers are called as face embeddings. In the last steps, these face embeddings are compared in Euclidean space. Different images of the same person tend to form a cluster. We can then compare the distance of any new face image with these clusters and recognize the person present in that image. Finally, to sum it up, face recognition pipeline consists of 5 steps. First, locate and extract faces from each input image. Then pass the extracted face thumbnail to the step number 2, which locates the facial landmarks. In step 3, these detected landmarks are used to learn affine transformation between face thumbnail and the template. This affine transformation is then used to warp the face thumbnail to compensate for head rotation. The output image of step 3 is then passed to step 4, where the image is encoded into face embeddings. The last step is where verification or identification happens. In this step, we check the similarity or differences between the encodings of two faces using different measures, the simplest being Euclidean distance. Let us now dig a little deep and learn how faces are detected. To detect faces, first convert the input image into black and white or grayscale. Then compute the gradient at each pixel. The gradient has magnitude and direction. It can be calculated by finite centered difference over the input image. The gradients calculated considering the neighboring pixels denote the transition or a change from light area to a darker area, and when calculated at every pixel forms the gradient map. But still, capturing gradient at every pixel is more detailed to be handled by our machine learning classifier. Therefore, we now divide the gradient map into smaller blocks of 16 by 16 each. The gradient in each 16 by 16 block is quantized into 9 bits based on the direction of gradients and are weighted as per the magnitude. Thus, each 16 by 16 block now contains histogram of oriented gradients, which is a 9-dimensional vector. And the whole image is now a simple representation that captures basic structure of the input image. Next, we can train and use a machine learning classifier like SVM to classify the input image as a face or not a face. We can use a sliding window over the entire image and pass that small window to the machine learning classifier and decide if face exists or not. The window with the highest confidence can be selected as facial area. So, in a nutshell, to detect faces in images, first convert the image into grayscale, then compute the gradient direction and magnitude at each pixel, divide the gradient map into 16 by 16 blocks. In each of these blocks, quantize the gradients into 9 bins as per their orientation and weight according to their magnitude. This gives you the hog representation of input image. Now this simplified representation can be used with sliding window to detect faces with the help of machine learning classifier like SVM. Let us now dig deep into face recognition with Eigen Fcaes. As we have seen in face recognition pipeline that a line image is encoded at step 4. But what if we just take an image as a big vector of numbers and then store it in a database or feed it to a classifier? Say if the aligned image is 512 by 512, which is around 262,000 pixels. This is very large vector. Storing many such images in the database will be difficult. Even if we somehow store them, the comparison with other faces will be slower and thus not be very useful in real time. Furthermore, gray levels are sensitive to noise and lighting conditions. Thus, we won't be able to match the image of the same person under different lighting conditions. So it is very important to represent the image with fewer numbers. Or in other words, we need to reduce the dimensions of the data. Principal component analysis can be effectively used for this purpose. First, collect all the gray levels of an image into a long vector U. Just unroll the image into a vector. If the size of the original image is m by n, then the vector U will have m times n elements in it. If we have p persons and n views of each person, we can form a data matrix A by stacking these vectors horizontally. The dimension of this matrix A will be mn by pn. Next, we can create correlation matrix L, which is given as A transpose. This is a square symmetric matrix and its dimensions are mn by mn. Since L is a symmetric, its eigenvectors will be orthogonal to each other. These eigenvectors point towards the variation in the data, and their corresponding eigenvalues quantify the scatter in that particular direction. Most of the variance in the data is captured by first few eigenvectors. Thus, eigenvectors of L forms a good basis for the whole space. And most of the data can be reconstructed back even if we consider only few top eigenvectors. Now, since eigenvectors form the basis, each vector U can be represented as linear combination of eigenvectors. Or in other words, any face U can be expressed in terms of these new basis vectors. We can write U as summation I is equal to 1 say n ai phi I, where phi I is the ith eigenvector. To express any face in terms of this new basis, we need to find the coefficients ai's. To do that, let's see what happens if we take ux, the unknown face, and find the dot product with the ith eigenvector. Replace the ux by the linear combination of eigenvectors as above. If we expand out the summation and take the dot product with phi I, we can see that most of the terms reduce to 0. Since eigenvectors of a symmetric matrix are orthogonal, the dot product of a distinct eigenvectors will be 0 and 1 for the dot product with itself. Thus, right hand side of the equation will reduce to ai, and we will have u transpose phi I equal to ai. So, to find the coefficients, all you need to do is to find dot product of a phase vector with ith eigenvector. So in this way, we can find all the coefficients and express any phase with the help of these bases or the eigenvectors as a vector of coefficients ai's. But since we know that most of the variance is captured by first few eigenvectors, we only need to calculate few coefficients ai's. Any phase vector then can be represented by these ai's. Thus store only ai's in the database rather than the image itself. Phase recognition can be done by comparing coefficients of input phase vector with the coefficients stored in the database. We are almost done. Just one computational detail. Now, A, that is data matrix, is mn by pn dimensional, and L, correlation matrix, is mn by mn dimensional. This is a very large matrix. Computing eigenvectors of a large matrix is time consuming. But on the other hand, if we consider A transpose A, then its dimensions will be Pn by Pn, and this matrix will be considerably smaller, and thus finding the eigenvectors of C will be considerably easier than that of L. The only question is that can we find the eigenvectors of L from the eigenvectors of C? And in fact, if alpha I is eigenvector of C, then A alpha I will be eigenvectors of L. Let us see how. By definition of eigenvectors, I can write C alpha I equal to lambda I alpha I, since alpha I is the eigenvector of C. C is A transpose A by definition. We can pre-multiply by A on both the sides. We can replace A transpose by L, which is nothing but correlation matrix. In this last equation, L is a matrix, A alpha I is a vector, lambda I is a scalar. We can see that the matrix L times the vector A alpha I returns the same vector A alpha I scaled by scalar lambda I. So we can say that A alpha I is eigenvector of L if alpha I is the eigenvector of C. Now let's see how to train the algorithm to recognize faces. First, create data matrix A from the training images. Compute matrix C from data matrix A. Compute eigenvectors of matrix C. Compute eigenvectors of matrix L from the eigenvectors of matrix C. Select first few significant eigenvectors of L. Once we select the eigenvectors, we can find the corresponding coefficients alpha I and represent each training image as the vector of these coefficients. We should then store these coefficients, which represent phase with fewer dimensions, in the database. For different images of the same person, the clusters will be formed in the coefficient space. For any new image, we can just compute the distance from the mean of these clusters for recognition. At the time of recognition, create the phase vector out of unknown image. Compute the coefficient vector by taking dot product with the respective eigenvectors of L. Compare these coefficient vectors with the coefficient vectors stored in the database based on Euclidean distance. Now this is one way to reduce the input image dimension and recognize faces. But there are better methods. One of them being LDA, linear discriminant analysis, where we minimize within class variance and maximize between class variance. The other is to use deep neural network to generate image encodings. Face recognition has obvious use in security, surveillance, and access control, but it can also be used to organize photo libraries, to find lookalikes in hospitality, recreation, and retail, also to count number of people. Well, that's it from me. If you have any questions, you can send a text message or you can email me at bokeydeshmukh, that is bokideshmukh@gmail.com. Thank you.